last time we were talking about antiderivatives of certain functions. So we basically kind of have to have that memorized or be able to figure it out. So what was one of the functions that we learned how to take their antiderivative of last time? Right. Try to answer this without looking at your notes if you can.
We learned to take the antiderivative of a power function, x to the n. And the antiderivative of x to the n is just 1 over n plus 1 times x raised to the n plus 1.
Okay, excellent. That's the power rule for antiderivatives. Good. Okay, what would be another function?
Another function would be a constant, so k. And the antiderivative of a constant is kx.
Okay, excellent. What else?
And then also we learn how to take the antiderivative of 1 over x, which is the natural log of the absolute value of x.
Okay, good.
And then we also, let's see. Oh, okay. Yeah, we learn how to take the antiderivative of e to the x. And that is just itself, e to the x. And then I think the remaining two were the trig identities. We learn how to take the antiderivative of, let's see, sine of x. And the antiderivative is negative cosine of x. And we also learn how to take the antiderivative of, let's see, I think negative cosine of x. The antiderivative of that would be, let's see, derivative of sine of x is cosine of x. So negative sine of x.
Like this?
Yeah.
Okay, that's perfectly true. That's perfectly true. I think this one, though, we're unnecessarily complicating. So what would be the antiderivative of cosine x?
Cosine x. I'll give this just sine of x.
Right. So what you said was correct. This is probably a simpler way to think about it, though.
Okay.
Okay, very good. There we go. Okay, that's a very good recollection of those ideas we were going over last time. Good. All right, tell me when you have that written down. Okay, we'll maybe go through this on my screen. Obviously, this is very similar to the problems that we were doing before, but there's a little bit extra here. Well, the first part of the problem is going to be very similar. We need to find a general expression for f. So how would you begin here to find the expression for f of x?
Okay, so we can take the antiderivative of f prime of x, and that will give us 1 half x raised x squared. So 1 half x squared plus 4/3 x cubed.
Okay, excellent. Plus c. That's good that you remember that. What does c stand for?
A constant.
Yeah, so we have to remember plus a constant. Very good. And how would you check this?
We can take the derivative of this. So this function f. So for the first term, 2 times 1 half is just 1, and then 2 minus 1 is 1. So we have just x.
Good. So is the derivative of this equal to this? Okay, good. Because what's the derivative of c?
0.
That's right. Okay, very good. So this is what we went over last time. But there was something that should have been dissatisfying to us, which is that we were never figuring out what C actually was on those problems. Well, in this case, there's now enough information to figure out what C is. Well, any ideas? What we're going to need then is we need to figure out C. And the way you figure out variables is by writing down an equation and solving for that variable. So we need another equation or another version of this equation. So can you see what's another equation we can write down now?
Right, so give us f of 2 equals 3, so we can set the equation equal to 3, so 3 equals 1/2 x squared plus 4/3 x cubed plus c. And then I believe now we can plug in 2 for x.
That's right. In fact, we may as well have done that from the start. Since you plugged in 3, we can plug in the 2. So this is the key step right here. So what does 2 stand for here?
X.
X. That's right. And what does 3 stand for?
Y.
Y. Although we're not actually using y on this problem. So what's another symbol we could say that 3 stands for? F stands for F. That's, you plug the 3 in for F here. Notice how these line up with each other. You plug the 3 in for F, and you plug the 2's in for X. Okay, very good. And now we can solve this using algebra. You can go ahead and do that on your screen, I guess.
Okay. Okay, so this is 4 times 1/2, 2, plus 8 times 4, 32, divided by 3. 8 times 4 is 32, plus c. Okay, so okay. So I'm going to change this to decimal and then change it back at the end. So this is 3 equals 12.66 plus c, and then 3 minus 12.66 negative. And then change this to a fraction. Math, fraction.
Since you approximated, that's probably not going to give you a very good fraction.
Okay. Okay, then I'll just not do that.
Well, okay, fair enough. So that's probably good enough for your course. So we can just stick with that answer.
I'm not sure, because one thing they are a little picky about are fractions versus decimals.
Okay,
so,
all right. Oh, in that case,
yeah.
then we'll do it that way. Okay, good. Then we'll go back and try to get an exact answer.
Okay. All right, so I'll just do it like this. One equals. Okay. Then 1 minus 32 over 3. 1 minus Okay.
Okay, good. Notice that to get a clean answer for the fraction, you have to use the full decimal expansion, 9.66666666667, right? If you round off, you're not going to really get the exact answer as a fraction anymore. All right, so it wasn't super hard to do this with fractions, especially using some of the tricks on your calculator. Good. All right, now we actually haven't quite answered the question yet.
Okay. So find f. Let's see. I'm not sure if I'm using this correctly or not, if I need to put a d or not.
So it sounds like you invented a new constant?
Right.
Okay, well, let's erase that d. Now, how can you check to see if your answer is correct?
If we take this derivative of this whole function f, we should get this.
Excellent. Good. That's partial checking. Good. What else do we have to check to make sure our answer is correct?
If we plug in 2
Right.
for x, we should get 3.
Check that.
2, 4, 2 plus 8 times. Okay. Yeah.
Okay. So does this expression make f of 2 equal to 3?
It does.
Notice that wouldn't work though if you added a plus d. So that's the way to answer your own question. Do we need a plus d? Well, no, that would just mess us up. If you added a plus d, then f of 2 would not be 3 anymore, unless d is equal to 0, in which case y included it all. Okay. After all, remember our first expression had a plus c, right? And our whole job here was to figure out the constant. Our whole job here was to figure out the constant, and we figured it out. What was the constant?
The constant was this value.
Negative 29 thirds.
Good.
So there's no point adding in a new constant that we don't know. We just figured out the constant. Okay, what was making you think that you might add a d? Well, there were maybe some other problems that we've done where we do have to add a d, but that was not what we were seeing on that particular problem. Okay, but overall, that was some good algebra, so I'll go back to my screen. It looks like we got that problem right. So notice the constant turned out to be negative. There's nothing weird about that. So now we would know basically how high this function is if we were going to graph it. By the way, so this was the information that allowed us to figure out the position of the function, right? What does this equation represent graphically? What does this equation represent graphically? Okay. What's the graphical interpretation of this equation?
Right. So when x equals 2, then y equals 3.
Good. That's good. You haven't quite put that in terms of the graph. Quite.
Okay.
What does this tell us about the graph of f?
Let's see. That the graph, there's a point on the function f at x equals 2 and y equals 3.
That's what I was going for. That's what I was going for. Good.
Okay.
So what that tells us is that 2, 3 is a point on the graph. That's that graphical interpretation I was going for. So you figured it out. 2, 3 is a point on the graph. On the graph of what?
F.
That's right. All right, let's try this problem on your screen.
Five. So 4 divided by 5. So that's equal. One-fourth divided by, wait, 6 to the 5th, and then we put 5 on the bottom. Yeah. Okay, and then let's see, guys. Okay. Wait, this is F, not F double prime. Okay, I think that's good.
Okay, that's good that you took a couple more seconds to check there, because that we want to get that label correct. Good. I noticed that you really took your time coming up with the 1/20th. You weren't sure about that, so you took your time. That's good that you took your time and worked it out off to the side. But since you weren't sure, what's something you could do here to double check that you got it right?
We could take the derivative of this.
Yeah, you don't need to take the derivative of the whole thing, because I think it was only that one term that you were unsure about. So let's check that one term and see what we get.
Okay, so 1/20th x to the 5th. We'll use a power rule. And 5 times 1/20th is just 1/4. 5 over 20, which is 1/4. And then 5 minus 1 is 4. So yeah, that's good.
Okay, good. Okay, so it was good that you took your time on that problem, but that was one thing I didn't. It looked like that you weren't maybe realizing that you could check your work another way by just taking the derivative. Okay, so that's right. I wanted to do this because remember on that last problem you weren't sure whether you should add a d or not, and what made you think you should have a d? Well, you were probably thinking of this type of problem. This is the type of problem where we need a d. Why do we need? So why do we need two constants here? Well, the point is, every time you take an antiderivative, you introduce a new constant. Every time we take an antiderivative, we introduce a new constant. How many times did we have to take the antiderivative here?
Twice.
That's why we had to introduce two constants. Why did we not need a d on the previous problem? We didn't need a d on the previous problem because on that problem we only had to take the antiderivative once. So that's how you can tell the difference. Okay, good. So that was a good process. You got the right answer. I'll go back to my screen. I did want to point out what's a more streamlined way to figure this out. So you did figure this out, but here's the method I would suggest for this. The method I would suggest is first use the constant multiple rule. And just pull the 1/4 out in front. And basically, that's not going to be part of the antiderivative now. Now, what's left is x to the 4th. What's the antiderivative of x to the 4th?
1/5 x to the 5th.
And what you're doing there, that was the purpose of reviewing this idea. Now we can just use this mechanical rule that we've memorized.
Okay, cool. That's much easier.
And how would you simplify this now?
1/20th x to the 5th.
So you should definitely do that simplification. You should definitely do that simplification, but we can do it in these two separate steps. Okay, so the logic that you went through was correct. However, you're going to have to take so many of these antiderivatives, it's good to have a more streamlined approach that can boost your confidence that you're getting it correct. So what we used here was the constant multiple rule. We pulled the constant multiple out of the antiderivative and just multiplied it times the antiderivative of x to the 4th. That's a big time saver. Okay, good, but we got that right in any case. Let me write this down. Okay, so going back, so what we're going to be practicing now, that was a little bit of a digression. I wanted to review when we needed the d. So the previous problem that we did was this. So remember, the key thing here was now we're going to go over problems where we can figure out the constant. By the way, notice on this digression problem, we could not figure out the constants. But now we're going to go back to the problems where we can figure out the constants. So we're going to do problems that are harder than this. How do you do all of these, though? The key is, how do you figure out the constants? You need some extra equations. You need some extra equations to figure out the constants. So they're going to give you some information that will let you write down extra equations. And then you can solve that using algebra. If you have one unknown, how many equations do you need to solve for that unknown?
If you have one unknown, just 2.
So how many equations do you need to solve for one unknown?
How many equations? Oh, wait. How many? I think 1.
Not 2. 1.
Right.
After all, that's what we took here, right? We had one unknown, c.
Mm-hmm.
And this gave us one equation. This gave us one equation with c that allowed us to solve for c. This gave us one equation for c, and that allowed us to solve for c. This is a little confusing because you might think that the x is an unknown. But when you actually plug into this equation, the x is not unknown anymore, right? And you might think that f is an unknown, but when you actually plug into this equation, f is not unknown anymore either. So we ended up with one equation with one unknown. Now, we might do some problems where there's 2 unknowns. How many equations do you need when there's 2 unknowns?
2.
2. Okay. So we might get to some slightly harder algebra where we need to solve 2 equations and 2 unknowns. It shouldn't be super hard, but we'll see if we can handle that. So the key thing for these problems is use this extra information to write down equations that will let you solve for the constant. Okay. And also, I'll just warn you, it's very important not to get confused between f, f prime, and f double prime. We have to be careful not to confuse f, f prime, and f double prime. That kind of crept up on us on this last problem, where for a moment we were accidentally labeling this as f double prime when it was really f. Okay, let me write this down then. Okay, try this problem.
Okay. we can plug this back into here. We should get this. Wait, no, we should plug this back in here. We should get this. So 8. Okay, I think this is right.
Okay, I don't think you've written down an answer yet. We saw again on that last test that they're picky about writing down the answer in the correct form, so that's something that would be good for us to practice.
Okay.
Okay, and did you check that answer?
No, I didn't.
It sounded like you were talking about checking it.
Right, and then I gave up.
Okay, let's go ahead and check it.
Okay. Okay, so if we plug in the x value, which is 2, we should get 4. So well, I definitely did something wrong, so this isn't right. That doesn't work. So f prime of x equals x squared minus 2. Okay. I'm not sure what I'm doing wrong because when I plug in 2 for this, I don't get 4.
That's right. So our original answer was incorrect. Did you check your work to see whether where you made your mistake?
Yeah, I don't see it.
Okay. Point to the equation that says 4 equals 1/2 times 2 cubed minus 2 times 2 plus c. That's the line where we made our mistake. So let's check that line. Okay. Was there any reason that you thought that was 1/2? Because even when you went back to check, you weren't catching that. Was that a careless mistake, or did you think that was 1/2 for some reason?
I think it was a careless mistake that
Okay. All right. In that case, we should have caught it when we went back to look at it again. I think maybe we just didn't take our time enough to check each of those steps. Okay. Anyway, this is the type of problem where you certainly can check your answer to see whether you're getting it right or wrong, and then we just need to go back and check each of those steps. Okay. Well, let's try again.
Okay. Okay, so we plug in 2, we should get 4. So, yep, that's right.
Okay, good. Okay. Okay. All right. So we saw it was possible to check our answer here if we make a mistake on these problems. I'll go back to my screen. When you checked your answer there at the end on the calculator, did you do that in one step or break it up into separate steps?
I did it in separate steps.
Okay, that's fine. I know a lot of people feel more confident on their calculator if they do it that way because otherwise it's hard to know when to put in parentheses. But I will just show you on a problem like this, we don't have any numerators that have to be put in parentheses or any denominators that have to be put in parentheses or any exponents that have to be put in parentheses. So we could just type it in. 1/3 times 2 cubed minus 2 times 2 plus 16 thirds. Oh, after those big words, if this better come out right. So let's see. Good. All right. Good. Okay. So anyway, I know oftentimes people are not very confident about doing things in one step on the calculator, but I thought I'd just show you that in this case, there's a straightforward way to do that. I think this makes it easier to check that you actually did it correctly because you can see the whole thing. Whereas if you break it up into separate steps, it's easy to miss if you made a mistake or to see where the mistake was. Okay. Very good. Let's see. Okay, so we got that correct. Oh, no, we got that incorrect, but I think we understood it conceptually. So we'll keep going. Let's see. Okay, well, this problem is similar to one we did before, but harder, a little bit different, a little bit harder. But instead of giving you a demonstration, I'm just going to let you give this a shot on your own. So try this problem and see if you can adapt our methods to try to work this out.
Okay, so f prime next is 8 f prime x equals 8x. So that means f of x equals 4x squared. Okay. So now we can what is this? 2. Actually, I think it's best if I stop here and then solve for this first. Let's see. 3 equals 1. Let's see. Negative 95. Okay. That means f of x equals 8x plus negative 5c plus d. Right now. Okay, so that means f of x.
Okay, so we made some mistakes here. You could catch your mistake by checking your answer. If you check your answer, you'll see you made some mistakes here. But to save some time, I'll just point it out. So let's see, where did we go wrong? First of all, I wanted to mention, you did catch this, but I wanted to notice that sometimes we have a habit here to leave out the plus c on this type of problem. I noticed that when you wrote down the f prime of x, at first you just wrote f prime of x equals 8x. Now you went back and fixed that and added the plus c, but it's important to put that constant in from the beginning. Okay, so let's see. What did you get as your value for c?
Negative 5.
Good. That's where we went wrong, though. That's correct, but what should we do with that? Where should we plug that in? Where should we plug in that negative 5?
Into f prime.
Okay, but we never actually wrote that down, and I think that ended up confusing us. So let's write down what happens when we plug that in.
I'm not sure how to write it down.
Okay, well, point to the equation that you're plugging into.
Right here.
Good. And what number are we going to plug in?
It's just negative 5.
And what letter are we going to plug that in for?
C.
So that's what we have to do.
Okay.
Okay. What was giving you trouble? You were probably given pause because you were asking yourself, what should I plug in for x? Well, at this point, we don't have any particular number to plug in for x. Remember, we want functions of x. This is supposed to be a function of x. So ultimately, in our answer, we don't want to plug in a number for x. Ultimately, our answer is supposed to still have an x in it. So do you see how that's a little bit of progress? Before we said that f prime of x was 8x plus c. But now we can be much more specific. Now we can say it's 8x plus minus 5. So that's an important step, to take that number that we're getting and plug that in. Why don't we simplify that expression for f prime a little bit? How could we simplify that expression for f prime a little bit? Okay, that's definitely a simplification. Minus 5 is certainly simpler than plus minus 5. Let's check that. How would you check if that equation if that value of f prime is correct so far?
We can plug in 1 and 3.
Well, let's see. Yeah, you could. That's right. What else can we do to check it?
Okay. We can also take the derivative of this, and we just get 8.
And do you?
Yeah.
But notice that you could have done that with lots of things. This could have been 8x minus 4, or 8x minus 12, or 8x plus 13. There's lots of things that would give us the right derivative, but now from the f prime of 1 equals 3, we also know that that constant should be minus 5. Okay, good. So now that we've written down, so point to the last equation we wrote down. That just in our work together. What was that?
Right here.
Yeah. Now what? What can we do next?
We take the antiderivative of this value of the function
Good.
f.
Good.
Yeah, and I mixed that.
So what went wrong the first time?
I just rewrote the first derivative.
So basically kind of what you did, yeah. So basically we were skipping some steps. Just writing down that new version of f prime, I think, makes it much clearer how we should take the antiderivative. All right, so what this extra step of writing down, I think, is what's going to clarify things for us. Okay.
So 2 over 2, 4 squared minus 5x. You already used C. D.
That's great. That's good that you didn't try to use C again, because we already used that up. Good.
Okay, so now we have this. Give us this. So we can just 2 equals 1 squared minus 4 minus 5 d 2 equals negative 1 plus d equals 3. Okay. So now it's finding f. So f of x over x squared minus 5x plus 3. If we take the derivative of this, we should get this.
Yeah, let's go ahead and do that check. So let's do the check.
Okay. Yep. That's true. Then if we take the derivative of this, should just get it. Should just get 8. Oh, that's true.
Good. So now you've confirmed that we did get, so maybe we can go back, put a check mark next to f double prime of x equals 8. We checked that, I mean in the original information.
Okay.
And there's 2 more things we can now check. So let's check those to make sure we got those right.
Okay. So one, 2 is 2, so there's f is here. So well. Just 4 minus 5 is 3. Negative 1 plus 3 is 2. Negative 1 plus 3 is 2. So that's true.
Good. What were you plugging in for x?
1.
So we should write that on the left-hand side of that equation too. Now notice in this case, now we can plug something in for x, because now we're plugging in a particular point. I guess that can be tricky to know when to write down the x and when to write down the number, but in this case we were definitely plugging in a number for x. Good?
Now we can do the same thing for f prime. So f prime 1 equals 8 times 1 minus 5. So that 8 minus 5 is 3. So that's true.
Okay, good. So that might be a good method on the test if you have time. You can certainly check your answers on these. We can always tell whether we got these correct. Okay, this gave us a little trouble, so let's review what was giving us some trouble here. First of all, remember, I think on these problems, you sometimes have a tendency to start by not writing down the constant. At first, you wrote down f prime of x equals 8x. And then later, remember, you have to go back and put in the plus c. So we need to put in the plus c from the beginning. And then when things really went wrong for us was after we got c equals negative 5. So what was the next thing we should have done after we discovered that c equals negative 5?
We should have checked it. Well,
I'm actually going for something different than that. What we should have done was plug that in.
Right.
Plug it into what?
Into f.
Now, we didn't know f then, so we couldn't plug it into f. Maybe point to where we figured out that c equals negative 5. Good.
Right.
Then what? What was the next step in solving the problem?
We plugged in first the first derivative.
Yeah, not f, but f prime. Notice how important it is not to get all those various things confused. Okay, so it looks like that's still giving us a little trouble. That's the part to really highlight there. So what do you do with the constant? What do you do with c once you figured it out?
We plug it first derivative.
You plug it back into the same, yeah. Well, basically, how do we know that's where we should plug it in? Because that's the only place that we've written a c, basically. We wrote a c as part of the expression for f prime, so now we can plug in that we know more about f prime. Before, all we knew was that f prime equals 8x plus a constant. But now we know that f prime equals 8x minus 5. And then once you wrote that, I think you were able to work out the rest of the problem. So that was the key step that was giving us trouble. Okay, I'll go back to my screen.
Okay.
Okay, let's try this problem.
Okay. So f prime of x will be 1 half x squared. Yep. Minus 4x plus c. And then if we take the derivative of this, it should give us x minus 4, so 2 times 1 half is 1. 2 minus 1 is 1, x. That's good. And then now we can take, now we can set this equals 2 equals 1 half of 1 squared plus 4 times 1 plus c. And then we get 2 equals 1 half. 1 half times 1 is just 1 half. Minus 4 plus c. So we get c is equal to 5 1/2. Now I'm going to check this right away. So now we can plug this in this side work. So f of f prime x is equal to 1 half x squared minus 4x plus 5 1/2. And then
Good. I think we're better off in this course. The way you've written that is what's called a mixed fraction. 5 1/2 is a mixed fraction. We'll be better off if we write our fractions as improper fractions, if you remember what that term means. So that's a single fraction rather than...
okay.
Your calculator can do that for you.
Right.
How do you enter 5 1/2 into your calculator?
5 times, 5.
Okay, that would certainly work. That would certainly work. That wouldn't work if you had, say, 5 1/3, though, or 5 1/7. What does 5 1/2 mean? How would you calculate 5 1/2 as a decimal on your calculator? How would you calculate 5 1/7? I'm sorry, I didn't hear what you said.
I don't know.
Okay, 5 1/2 actually means 5 plus 1/2. I think if you think about that, you'll see that's right. 5 1/2 really means 5 plus 1/2. Do you see why that's true? Mm-hmm. So that's how we can enter it into the calculator.
Okay.
And then you can go back to the fraction menu on your calculator.
11 halves.
Okay, good.
Okay. So, two, 8, 11, 6. Okay, that's good. 3.
Okay, that's good. So point to where you found that c equals 11 halves. Just point to where you have written down that c equals 11 halves. What was the next thing you did after you figured out that c equals 11 halves?
We tried to prove that, so we did this side work over here.
Good. Although that was kind of just a digression. It is true that you checked your work, but the important thing you did is that you plugged c in. You plugged 11 halves in. Where did you plug it in?
Into f.
Well, that wasn't what we did immediately after finding c. Where did we plug? Because we didn't know f yet. When you found that c was 11 halves, you didn't know f yet. So where did you plug the c in?
Into the first derivative.
F prime. That's right.
Right.
So my point is, when you figured out f, you were kind of using the wrong equation to figure out f. So notice there's a version of f prime on the left. Can you point to that version of f prime on the left? That's what you took the antiderivative of, right? You took the antiderivative of that. But there's a better version of f prime that we should have taken the antiderivative of instead. What's the equation we should actually have taken the antiderivative of? The f prime on the right. Do you see what I'm saying? Point to that. That was the whole reason why we plugged it in. Checking was just a bonus. The whole reason we plugged it in was so we would have a more concrete equation to take the antiderivative of. Maybe put a box around that f prime. Notice that that f prime is done. We can put a fork in it. Let's put a box around the whole equation, maybe. That equation is done. There's nothing more to figure out about that equation. So if we want to figure out f, that's the equation to use to figure out f. And then if you had done that, you could have kind of saved yourself a step. Instead of first writing down cx and then plugging in the 11 halves, there's no reason to be writing c anymore, is my point. There's no reason to be writing c because we know what c is. So why don't we go ahead and erase that line that we didn't need? And that arrow you wrote is a good one because that shows that we figure out f from that version of f prime. So that's not exactly a mistake because you did end up with the right answer here. But I think this is a better way to do it. Okay, so the fact that you checked there was just a bonus. That was not the main reason we plugged in the 11 halves. The main reason we plugged in the 11 halves was because we wanted a nice clean version of f prime to take the antiderivative of. Now, it sometimes might happen that you don't know c when you take the antiderivative. So it might sometimes happen that you have to keep just lugging a c around. If we didn't know what c was, we just have to keep lugging it around in the new f equation. But since if you do know what c is, it's better just to get rid of that and just plug in that number. Okay. Cool. All right, so now we can continue.
Yeah. I was wondering why I wanted to keep putting c. Just, I guess, a mistake. Okay. Oh. All right, so now we have a 0. Well, that's 0 plus 0 plus d. Oh. T equals 1, so now let's find f. As our as I'm writing this, just a quick question. I notice sometimes in the textbook, for example, they use capital F to I'm not sure why they use capital F. Is it just different notation?
That's a good question. That's a good question. So we'll finish off this problem, and then I'll try to remember to come back to that.
Okay, cool.
Okay. So
I made a mistake.
Yes, that's good that you check that. Those mistakes are just everyone makes mistakes. The important thing is to check. So let's review this again. Go back up to where you figured out C. Write down point to the line where you got your C.
Right here.
Yeah, where did the C come from? What equation did you use to figure out what function did you use to figure out C?
The first function we take the antiderivative of.
So what's the name of the function that you used to figure out C?
F prime.
And then what did you do once you figured out C? What was the next thing we did once we figured out C?
We plugged C into we plugged C into the antiderivative of f prime of x.
You mean F?
Which
right. Now that doesn't quite make sense because we didn't know F yet. Where did we really plug C into? What was the first place that we plugged in a C?
Up here?
Yeah, what's the name of that function?
F prime?
Not F.
Okay.
So it looks like we're still getting kind of confused about that. Then we used that to figure out F. We couldn't plug C into F yet because we didn't know F yet. But let's go through this whole problem again so that we have our bearings here. Let's go back to the beginning. Let's see. What function were we told in this problem? What's the name of the function that we were told?
They gave us f double prime of x equals x minus 4.
So we knew f double prime. So what was the first function that we had to figure out?
We had to figure out f prime.
Yeah, we had to figure out f prime. Now, the first time we figured out f prime, we only partially figured it out because we didn't know what its constant was. So point to the first time we figured out f prime. Notice that was only a partial success because we didn't know what the constant was yet. So then once we knew, point to where we figured out the constant. Once we knew what the constant was, where did we plug that in?
Okay, back into f prime.
So that we would have a complete answer for f prime. Then we plugged it in. Now we know completely. So just to review that one more time, since that's giving us some trouble. What was the first function that we were told in this problem?
F double prime.
And then what was the first function we tried to figure out?
F prime.
But notice there's a two-step process for figuring out f prime. There's a two-step process. Step one is you get the general antiderivative. Point to the general antiderivative.
Right here.
Yeah. And then step two is figure out the particular antiderivative. Point to the particular antiderivative.
Right here.
Good. And then what? Once we knew exactly what f prime was, what was the next function we tried to figure out? Sorry, go ahead and write whatever you want, but what's the next function we tried to figure out after we knew exactly what f prime was?
So next we find f of x.
Next we find f. Now let's scroll down a little and you can see we went through that same two-step process again. Because notice the first time we found f, we only found a general antiderivative. Right? The first expression for f was only general. Why am I saying that it's general and not specific? Because we didn't know what the constant was yet. So first, we only knew the general form for f. So the next thing we had to do was figure out the constant. And then what did we do with the constant once we knew it?
We plugged it back into f.
So that then we knew the particular antiderivative. So we had a complete form of f. So it was the same two-step process for figuring out f prime and then for figuring out f. That's what I think has been giving us some confusion here.
Okay.
All right, so hopefully that helped us to get our bearings on this problem somewhat. Okay, let's check that answer. How would you check that?
Okay, so let's see. Well, first we can take the derivative of this, of f, and we should get f prime. So if we do that, we get 3 times 1, 6. Which is...
Let's go ahead and write that down.
Okay. Yeah, I'll just do all the work here. F prime of x equals 1/2 x squared 4x.
Good. Good. And just take the second derivative. Good. Now we should be able to go back to the 3 pieces of information we were given at the start and check all 3 of those pieces of information.
Okay, so they gave us f of 0 equals 1. Okay, so f of 0 equals 1. So here's our complete form of f. If we plug in 0 for f, 0
For
minus for x, 0 minus 0 plus 0 plus 1 means f of x equals 1, which is true.
Good.
And
So we can put a check mark there to show that we checked that.
And then f prime of 1 equals 2, so there's f. That's our complete form of f prime.
That's right. But now we've rewritten it down below. So that's where we should be checking it now.
Okay.
To be sure that we want to be sure that the f prime that we get from our answer is correct.
F prime of 1 equals 2. Okay, so plug in 1 for.
So we should be able to check that in one step on your calculator.
Okay. 1 divided by 1/2 times 1 squared minus 4 times 1 plus. I'm just typing in to make sure I can do this correctly in the harder problems. So plus 11/2. That's not right. 1/2 times 1 squared minus 4 times 1 plus.
Oh, maybe we made a mistake. That's a good thing we checked.
Oh no, I added an extra digit. Okay. 1/2 times 1.
Yeah, I guess we must have made a mistake. I'm sorry. I should have caught that earlier. I shouldn't have let us go on so long. So is that coming out right?
Yep. Yeah, it does. No,
it does?
I typed in an extra digit on a value.
How can that be right? Oh, I forgot the 1/2. Okay. So 1/2 minus 4. Gotcha. Okay, good.
So that's good. So I think we checked all of our checkable.
So let's see. Did you put the check mark next to that? And then what was the third piece of information to check? What was the third piece of information we were given at the start?
The f double prime equals x minus 4.
That's right. So we should check to make sure that that really came out right.
Yep, this was
okay. So then we can go back and put that check mark there. Okay. All right. All right. So that would be a good question to go back and try again. I'll go back to my screen. Okay, well, this problem has some similarities to the ones we've done before. It also has some differences, so we'll have to adapt somewhat. But I'll give you a chance to try this. So give this a shot, and let's see if we can adapt to work out how to do this problem. Oh, nope. Sorry, let's go back to my screen. You had asked about those capital letters, so we may as well discuss that. So let's see here.
Yeah, I've seen it done a few different ways, so I'm quite sure.
So what would this be?
This would just be x squared.
How would we put this into words?
The derivative of 1/3 x cubed equals x squared. Or the antiderivative of x squared is 1/3 x cubed.
Good. Now, how could we re-express this using function notation? Well, who's the original function here? When we write this sentence, would you agree we're kind of assuming that we started with 1/3 x cubed and took its derivative, right? So we could say that the original function here was f of x. And then what would be the function notation for x squared?
F prime of x.
So this is how we write it when we're treating this as the original function. And then this is kind of the derived function. That's why it's called the derivative. It's derived from f. But now, how could we use function notation to translate this sentence? Well, when you say the antiderivative of x squared is 1/3 x cubed, who are we kind of treating as the original function?
X squared.
Yeah, we're kind of starting with x squared and taking its antiderivative. So now it would be natural to call x squared f of x, because we usually use f, little f, as our original function, right? We usually use little f as our original function. Notice that now these two lines contradict each other. They're two alternative ways of writing this. If you're treating 1/3 x cubed as the original function, that's the natural one to call little f. But if you're treating x squared as the original function, that's the natural one to call little f. But now, what can we call the 1/3 x cubed? Would you agree it would be totally wrong to call it f prime? Because it's not the derivative. So we need a new notation. So what your textbook does is it uses a capital letter for antiderivatives. Okay. That's the answer to your question. Your textbook uses capital letters to indicate antiderivatives. That was kind of a long-winded way to answer your question, but I finally got to the point. The point was that your textbook uses capital letters to mean antiderivatives. So what does a capital F mean? Capital F means this function is the antiderivative of little f. That's the convention they're using.
Okay.
So that was a good question. That's an important point. So what do you think this would mean?
The antiderivative of g of x.
Yeah, so now we have to be careful because this is g. You have to say the antiderivative of little g.
Little g of x.
Yeah. So one thing we've seen is that mathematicians make a really big deal about capital and lowercase letters. They make a bigger deal about it than your English teacher. So to a mathematician, a little f is a totally different thing than a big F. They're totally different names. You might as well call this function Bob and this one Alice. They're totally different names. So we have to be careful, and when necessary, we have to say big F or little f. So what is this function?
Big h of x is the antiderivative of little h of x.
There you go. That's right. Okay, so I think that's the answer to your question. Your textbook uses capital letters to indicate antiderivatives. They use capital letters to indicate antiderivatives. Well, notice now we have two different ways to indicate kind of an antiderivative. If you start with the original function, then its derivative is f prime. But if you start, I'm not quite putting this right, but if you start with x squared here, then its antiderivative is f. I didn't quite put that into words right, but I think you see what I'm saying. Okay, so let's go back here before I confuse myself anymore. So, all right, here's the problem that we were trying to do. So I don't think for this particular section of the book that we need that capital and lowercase notation, so I hadn't been introducing it yet, but that's what that means. Okay, so for this section, I think the notation we've been using is the best. So let's try this problem now. Again, this problem is similar to what we did before, but somewhat different. What we're going to have to adapt somewhat.
Okay. Both of these were F right here?
Yes, that's
F?
correct.
Okay.
That's why we're going to have to adapt.
Okay.
That's
All
going to
right.
double check.
So f prime of x is the minus sine of x. So f prime of x equals what gives us sine of x? What gives us negative sine of x? Cosine of x. Let's see. So we don't have anything yet. So f of x. That gives us cosine of x. That's sine of x. What gives us negative sine of x? Cosine of x. What gives us cosine of x? Sine of x. Okay. So I think sine of 0 is just 0, but double check. So d equals 1. And I think we have to, if d is 1, we know what x is. So 2 equals the sine of pi over 2 plus c times pi over 2 plus 1 sine of pi over 2, 1. And then okay, so 1, 0, c equals 0. Well, all right, so we can check this. I'll take the derivatives first. F prime is derivative of sine of x is just cosine of x. This is 0. I guess I made a mistake. We should, well, we can't write the simplest form yet. Or we can afterwards. I don't know. Okay, f double prime. Derivative of cosine is negative sine of x. Okay, so that's good. That was good, and that was good. And f of 0 equals 1, so here's f. Sine of 0, f of 0 equals 0 plus 1, which equals 1, so that's good. And then f of pi over 2 is equal to sine of pi over 2 plus 1, which is equal to 2. So that's good. Okay, I think that's good. So my answer is, where's f at? My answer is this.
Okay, let's talk about those steps. So let's see, what was the original function that you were told?
F double prime.
Good. And then what was the first function that you figured out?
F prime.
Right, because that's the antiderivative of f double prime. Notice that at first, what you figured out was just a general form, the general antiderivative of f double prime. And then you did something that was good here. You realized that at that point, there was no way to find that specific antiderivative. You realized that at that point in the problem, there was no way to figure out c. That's how this was different from the earlier problem. So that's good that you saw that and adapted to that. In the previous problems, we were able to immediately figure out what c was. But it's good that you realized that in this case, we had to postpone that. We just had to lug the c around. So there was, so we were only, at the beginning, we were only able to find the general antiderivative of f double prime. We weren't able to find the particular. So what did you do next after you figured out f prime?
Okay, so once we figured out f prime, we figured out f.
By taking the antiderivative of f prime. Mm-hmm. Good. And that started as being only, that started as having a bunch of unknowns in it, c and d. So then one thing you have to do here, then you use two pieces of information. F of 0 is 1, and f of pi over 2 equals 2. One thing that's important here is it's best to use those in the best order. If you had started by using f of pi over 2 equals 2, you would not have been able to get a clear answer yet at that point. If you had used those in a different order, you would have not had a clear answer. So what would you have done? What should you have done if you started by using f of pi over 2 equals 2 and that doesn't give you a clear answer? Well, hopefully you would not despair. Hopefully you would just go to the other piece of information and try f of 0 equals 1. So what I'm saying is you can use your judgment to decide what's the best order to use the information you're given. But if you happen to make a bad judgment call, you don't have to give up. You can just move over to the other piece of information and see if that's more helpful. Okay, so you got that point to where you saw that d equals 1.
Right here.
Good. Now what's the next thing you do after you figure out that d equals 1?
Now we plug d into f.
Good. Except you didn't exactly do that. You kind of skipped over that step. You didn't actually write down a new version of f where you had plugged in the d. That didn't mess you up on this problem, but it could have confused us. So we should have added that as a separate step. You can write that maybe, maybe write that up above. See your work on the right? There was a step you kind of skipped there. You should have written down our new expression for f now that we know d. Good. It's good that you haven't plugged anything in for c yet, because we didn't know c yet. So that's the step that keeps giving us some trouble, plugging in the constants once we know them. Once we know the constant, we should plug that in. So now you kind of plugged it in the next line, right? In the next line, you can see you do have a plus 1. But I think it's better to write the general form first there. So after all, what was the function that you used to figure out d?
The function to figure out d was f.
Yeah, and then once we know d, that gives us a more specific form of f. Then we can plug that right back into f to get a more specific form of f. And then that's the equation that we should be plugging into then to find c. And that really is what you did. You did plug in for D there, but it's better to write that out separately the way we have it now. Okay, so then you worked out what C was, and then what do you do with the C now that you figured out the C?
So now that we have the C, we can plug C back into F
And you
as
did do
well.
that. You did do that.
Mhm.
You did do that, and you got the correct answer. Okay, good. So that was right. I noticed that when you were checking your work, you didn't sound very happy. You sounded like you were thinking you might be making some mistakes when you were checking your work. But it all worked out okay. I think one thing that might have been confusing you is when you get to the point where you're checking your work there, I think you should start then ignoring your intermediate stages. So how do you check your work? Well, now that you know F, you should just now, from that F, figure out what F prime and F double prime would be given F, and then don't check that against your intermediate work in the middle of the screen. Just check it against the 3 pieces of information you were given up front. If it matches those first 3 pieces of information, then we know that the middle work is right. So we're not checking our answer against our work. We're not checking our answer against our work. We're checking our answer because our work might be mistaken. Do you see what I'm saying? It's pointless to check your answer against your work because the work is what we don't know. We don't know if the work is right or not. What's the part of the problem that we know is right? Well, we know that the information we were given at the start was right. Unless the problem was miswritten, that must be right. So we want to check our answer not against our work, but against the 3 pieces of information at the start. And you sounded like you weren't quite certain about that, but you did do that correctly. You did do that correctly, and you ended up seeing that you had gotten the right answer. Okay, so overall, that was a success. You got that right, and you used overall a good approach. I had a couple of recommendations on that problem, but overall, that was a good way to adapt to a new problem. This problem was trickier and different from the problems that we did before, but you did do what I asked, and you did adapt to that and work it out. So that's good. I'll go back to my screen.
Okay.
Okay, so I think we've made some progress on that. So let's talk about something a little bit different now. Let's see. Okay, try this problem.
Okay. G of A. Okay. G squared and then prime G of A. Okay. So G prime of A equals 1/3 A cubed plus C. Okay. And G of A was 4. So 1/3 times 1/4 A to the 4th plus CX plus D. I take the derivative for 1/3 A cubed C and then A squared. Okay, cool. I think that's good.
Okay, so what is the independent variable in this problem?
Let's see. D.
No. Are you familiar with that term, independent variable? Have you heard that?
Yeah,
So
I
the
have.
independent variable is the input to a function. It's the variable that goes on the horizontal axis. And the dependent variable is the output from the function. It's the variable that goes on the vertical axis.
Okay.
You can see that D is wrong because is D a variable or a constant?
A constant.
So it can't be the independent variable, can it? Because independent variable has to be a variable. Okay. So let's try again. What's the independent variable on this problem?
A.
That's right, A. A is the input to the function. And what's the dependent variable?
Well, A as well. A squared.
A squared. Yeah, what's our symbol for that? Well, what I was going for was G. If you were going to graph this function, what variable would go on the vertical axis?
G.
Yeah. Now, you wouldn't graph the G double prime. You would graph the G function, probably. Okay. In any case, there shouldn't be any x's running around, is my point. Okay. So that one we somewhat got incorrect because we invented a new variable that wasn't relevant for the problem. In this problem, what's the independent variable?
The independent variable is A.
Not x. So we're taking the antiderivative with respect to what?
A.
Yeah, not x. So what's the antiderivative of c with respect to a?
CA.
That's right. What would be the antiderivative of c with respect to x?
CX.
Good. I guess that's a little unfair because we haven't really been talking about that with respect to terminology in this section. But you might remember we used those terms when we talked about derivatives. We talked about how technically whenever you take a derivative, you have to be taking the derivative with respect to a variable. Well, the same thing is true for an antiderivative. When you take an antiderivative, you're taking the antiderivative with respect to some variable. For example, notice here you have like g prime. Prime means derivative, but we're taking the derivative of g with respect to what?
A.
Right, so when we take the antiderivatives, that also has to be with respect to a. Okay, I'll go back to my screen. Well, you can see how that's a very easy trap to fall into because 98% of the problems are about x. Since 98% of the problems are about x, it's easy to kind of just keep writing x on autopilot without even thinking about it. So the lesson here is we can't just write down x on autopilot. We have to write down x when that's the appropriate variable, but write down something else when that's an appropriate variable. Our table here then could be misleading. We happen to use x, but this table could work for other things. For example, suppose the function was a to the n. What would be its antiderivative?
1 over n plus 1 times a raised to n plus 1.
In this particular example, are we treating a as a variable or a constant?
A variable?
Yeah, that kind of breaks the normal pattern, but we must be treating it like a variable or it couldn't be a power function. Okay, good. And what's the antiderivative of k with respect to a?
Ka.
Yeah, here we were assuming we were taking it with respect to x when we wrote this down. Okay. Now let me change that to this. Okay, let's try this problem.
Okay.
Okay. In this case, all we can do is find general antiderivatives. There's not enough information to find particular antiderivatives. Good. How would you check your answer?
You can take the derivative of h, and we should get h prime.
Good. Now, we would take the derivative with respect to what?
Q.
Right. Not with respect to x, say. Okay, good.
Right.
So what's the independent variable here?
Q.
Good. What's c? Is that a variable or a constant?
A constant.
And d?
A constant.
Okay, good. So I just wanted to review. Most of the examples we've done have had an f and an x, but you have to be able to adapt to different letters being used as well. Very good. I'll go back to my screen. There was no particular need there to use a capital Q. I had written down a lowercase q, but if you find it easier to write the capital Q, that's okay for this problem as well. Mm-hmm. Okay, good. So I'll go back to my screen now. Okay, so that was just one point that was important to cover. Let me write this down. Let's try this problem. Whoops, I didn't quite write that down right. That should be. Okay, like this. Let's try that.
Okay.
Okay, so what's your answer?
S prime of t equals 2x plus 3.
Okay, that's excellent. That's a good answer. Now, that was a good step. That's probably not the best label to give the 2x plus 3 in our answer, though. What's the best label for the 2x plus 3 in our answer?
2t plus 3.
Oh, okay. Well, I hadn't even noticed that. All right, yeah. All right, so I didn't notice that, but we messed that up. Yes. Our first answer was totally wrong. I guess this is what we were just talking about, right? We were just talking about how it's easy to go onto autopilot and just start writing x's. So I guess that's what happened to us here. And I guess I was on autopilot too because I didn't notice that you had done that. So we both have to get off of the autopilot and make sure that we're checking to make sure we're using the right variable here. I can see how that's tempting because we've used x's so often. But what's the independent variable on this problem? T, not x. What does the t stand for?
Time.
Yeah, so you can see why it's very logical to use t on this type of problem and not x. Okay, so it looks like we messed up our first answer. Okay, now that we have that right, I still was going for something in addition to that. What's the best label for that function? What's the best name of that function, 2t plus 3? One good name is s prime. That's a good name. One good name for that function is s prime. Yeah. After all, that's what the question was asking for, right? So that might be the best way to write your answer. Okay, good. Although I'll go back to my screen now. Oh. Okay. Well, this is embarrassing. Okay, so I was just criticizing you for making this mistake, And I totally made the same mistake here. So I was the one that screwed up here. This is kind of mortifying. So I was the one that was on autopilot. I wrote the whole thing here with x's. So no wonder you put in the x's, because the problem was totally screwed up from the start. Okay, well, that was just a demonstration to show you what you should not do. You should not be on autopilot like I was there. Instead, you should be engaged and realizing that what's an independent variable for this function? T. Okay, so it's no wonder your answer had an x in it, because I screwed up and put an x in this function. But that didn't make any sense, because this over here was a t, so to match up, this should have been a t over here. All right, so I will have to be more careful about that as well. All right, so let's see. What do we have here? What velocity of the particle at any time t? Okay, so anyway, now we've got all those mistakes cleared out of the way. We got this answer. Now I think the best way to write the answer then is this.
Okay.
If you remember, another mistake. All right, if you remember, those are the symbols that we were using when we covered this earlier. Okay, hopefully now we've got this correct. Okay, now this was a good step. So what's the relationship here between S and V? How would you describe the relationship between S and V in words?
Okay. The first derivative of the position function is the velocity.
Good.
At any given time.
So I'll just say the derivative of S is V. Good. Now what's another way to describe the relationship between S and V in words?
Okay. Let's see. S is the antiderivative of V.
Okay, very good. That was kind of a vague question, but you guessed what I was going for there. That's right. So we can also write that as, say that one more time.
The antiderivative of V is S.
That's good that you paused and make sure that you got that in the right order. You wouldn't want to say of S is V here. Okay. So this is obviously, I think you remember, this is a topic we went over for one of the earlier exams in the course. In the earlier exams, we talked about the relationship between position and velocity. And what we learned earlier is that velocity is the derivative of position. And I think that's what you were remembering when you solved this problem. Notice I didn't ask you for the derivative, so you must have been remembering what we talked about earlier, and you must have remembered that velocity is the derivative of position. So that's good that you recalled that. Now we can apply to this the new stuff that we've gone over. And now this tells us we can also express this in terms of antiderivatives. So what we saw earlier is that when you know position, you can figure out velocity. But maybe when we know velocity, we can figure out position. Scientists always like to be able to move in both directions. Okay, good. Let's try to get this right. All right, let's try to get this. All right. I made a change here. Okay, I think I wrote that correctly. Let's try this.
So Vt equals 5 minus t squared, then S of t equals 5t minus okay. All right, so now we okay, and then if we plug in okay.
Okay, that was a good process. You even checked your answer at the end. Excellent. Good. And you put in your check marks. Excellent. Okay, so that's a good process and a good way to attack this. Now, at the end there, you found S prime. And what's another name for S prime?
S prime is also V of V.
Yeah, so you saw that since you got S prime equals 5 minus t squared, that matched up with the V equals 5 minus t squared. Okay, so this is, again, something we don't focus on too much in this course, but this is kind of like a practical use of all these antiderivatives. So this is a practical use in physics. You can maybe imagine that there might be a situation in physics where you knew what the velocity of an object would be at every time, where you knew what its velocity would be. Well, it turns out then that if the physicist knows about antiderivatives, they can figure out the position of the object at every time. So this is I guess, the first time that we've seen what the practical use of antiderivatives is. Mostly we've been focusing on the mechanics of antiderivatives, but this is almost like a little word problem that shows the practical use of antiderivatives. If you know the velocity of a function, you can use antiderivatives to find the position. If you know the velocity of the particle, you can use the antiderivative to find the position of the particle. It's important to keep reviewing this material. Some of these problems we missed, and some of the problems we got right, but we weren't confident. So actually, I would say that maybe is the top priority, to redo the questions that we just did to make sure you're very comfortable with this.